Assalamu alaikum. Hello everyone. Today we start our next topic, study of different combinational logic circuits. Combinational logic circuits are classified into arithmetic, such as adders, arithmetic circuits, adders, subtractors, multipliers, compare circuits or comparators. The second type, data handling, combinational logic circuits. These include multiplexers, demultiplexers, encoders, decoders. Third type, code converters, BCD to XS3 code conversion circuit, and vice versa, BCD to gray code, and vice versa, 7-segment decoder. And the last group, storage devices such as ROMs, PLAs, and PALs. These are known as mobile logic devices. Now we will go on detail and on this, and we start with the group adders and subtractors. There are different types of adders and subtractors: half adder, half subtractor, full adder, full subtractor, adder subtractor, binary parallel adder, BCD adder, carry propagation adders. Half adder is used to add 2 bits and outputs the sum and carry. Half subtractor is used to subtract 2 bits only and output the difference and the borrow. Full adder is used to add 3 bits and outputs the sum and carry. The same for full subtractor. Adder subtractor is a circuit used to add or subtract according to the command add or subtract. Binary parallel adder is used to add 2 binary numbers, for example 4-bit or 8-bit number with another 8-bit number. BCD adder is used to add 2 decimal digits coded in BCD. And the carry propagation adders are used to solve some problems in the binary parallel adder and to speed up the process of obtaining the sum. We start first by half adder. The general block diagram or graphic symbol is like that. Half adder have 2 inputs and 2 outputs. The first output is sum, sums the 2 outputs, and carry if there is a carry when summing these 2 inputs. A truth table for half adder, we have 2 inputs A, B. We state all on the truth table 0, 0, 0, 1, 1, 0, 1, 1, and the outputs are sum and carry. As you see, if we add 0 and 0, the sum is 0 and carry is 0. 0, 1, the sum is 1 and no carry. The same is for 1, 0. However, if we add 1 with 1, we have a sum 0 and a carry equals to 1. The sum is equal not AB, sum equal not AB or A not B, which is well known to you, A exclusive or B. No simplification is can be done here. The carry only when we add 1 with 1. So carry equals A and B. This is the logic circuit. We have exclusive OR for the sum and and gate for the carry. Next we move to half subtractor. It's used to subtract 2 bits and outputs the difference and the borrow. So this is the graphic symbol, 2 inputs and 2 outputs, difference and borrow. 0 minus 0, 0 and no borrow. 1 minus 0, 1 and no borrow. 1 minus 1, 0 and no borrow. However, here, when we subtract 1 from 0, we have to borrow. We have to borrow. So the borrow is 1. But the borrow makes this 1, 0, and 1, 0 minus 1 is equals to 1. Again, the difference is equal, not x, y, or x not y, which is the same expression as in the sum. Difference equals a exclusive or b, while borrow is 1 only here when x is 0 and y is 1. This is the only case we need borrow, so it is equal to not x and y. This is the logic circuit for the half subtractor. Now we move to full adders. Full adder is a combinational logic circuit used to add 3 bits together and outputs the sum and carry. You see, when we add numbers to numbers, at any stage we are adding the 2 bits from the 2 numbers, A and B, for example. But we need to consider the carry from the previous stage. So we need a circuit that adds 3 bits together and generates the sum and carry to the next stage. So the circuit that adds 3 bits together, AI, BI, with a carry in and outputs the sum and carry out is called full adder. The truth table for full adder, if we have inputs AI, BI, Cn, if we add 3 zeros, then sum 0 carry 0, 0, 0, 1, sum 1 carry 0, the same for 0, 1, 0, and for 1, 0, 0. But if we add 0, 1, 1, then the sum is 0 and the carry is 1. And the same if we add 1, 0, 1. If we add 1, 1, 1, 1, 1, and we have a carry also 1, then the sum is 1 and we have a carry out. So the sum is 1 and the carry is 1. From the truth table, it's very easy to obtain the sum and the carry out expressions. Sum equals to min terms 1, 2, 4, 7, and carry to min terms, as you see, 3, 5, 6, 7. Now, using K-maps, sum equal the min term 0, 1, 2, 4, 7. Here is the sum. Here we cannot simplify, so we cannot group anything, so we write the sum as not A, not B, C, or not A, B, not C, or A, not B, not C, or A, B, C. This equation can be simplified as follows. Here, not B out, and we have A, Cn or ACN, plus or B, AC, or not A, not C, not B. This is exclusive OR A and C, and would be this is exclusive OR A with C. So finally we can see that sum equals A exclusive OR B exclusive OR C. This is the expression for sum. Next, the expression for carry. Since carry is equals to midterms 3, 5, 6, 7, here 0, 1, 2, 3, 4 here 0, 5, 6, 7. So we can group these two together, and these two together. And the expression, the minimal expression for the sum is AB, BC, ACN. The full logic circuit for the full adder, we have inputs ABC, the sum is exclusive OR, and this is the expression for the carry. So this is the logic circuit for full adder that adds 3 bits together and outputs the sum and the carry. IBM designed in 1970 a circuit how to build a full adder from 2 half adder. So the first half adder we apply A and B, to the second the sum with C, and the two carries are OR to generate the carry out, and the sum from the first half adder is exclusive OR with the carry in to output sum. So this is the design of full adder using 2 half adders. For subtractor, we subtract 3 bits to generate difference and borrow. Although full subtractor are not used as a separate circuits, usually we perform subtraction in computers using adders. However, it's not bad to get an idea what's the full subtractor. We are subtracting, this is a stage. We have to consider if there was a borrow from this stage and if we need to borrow from the next stage. So if we subtract here, borrow out, borrow in, borrow in. Using this, you can derive and understand the truth table. For example, if we have 1, 0, and there was no borrow from this stage, then 1 minus 0 is 1, and there is no need to borrow from the next stage. If we are subtracting 1, 0, and there was a borrow from the previous stage, so the borrow from the previous stage change this bit to 0. So 0 minus 0 will be 0, and there is no need to borrow from the next stage, etc. According to this logic, you can obtain the truth table for the full subtractor, AB borrow in, difference borrow out. And from the truth table, you can write the expressions for difference and borrow. Here we have the difference, and we can simplify it in this form or rewrite it in this form and obtain that D equals AI exclusive or BI exclusive or borrow N. We should note that this is the same expression as for the sum in full adders. The borrow out, the equation for borrow is Bn or not AB or not AB, not B. This is the logic circuit for full subtractors. Now, binary parallel adder. Full adder, this is the circuit full adder, is capable of adding 2 bits with a carry and generate the sum. This is bit AI, BI. This is a carry in and this is a carry out. This is full adder. So one full adder can handle 2 bits and a carry from the previous stage to sum them, these 3 bits, and outputs the sum and a carry. And it cannot be used to add 2 numbers. We need to add 2 numbers, A4, for example, A3, A2, A1, with another number B, B4, B3, B2, B1. Do you see, for example, in this stage, we need to add A2 with B2, with the carry from the previous stage, and output the sum and a carry to the next stage. So in each stage we need full adder. Binary parallel adder is a circuit that adds 2 binary numbers. For example, we need to add a number A, a 4-bit number A, to a 4-bit number B. Then we need 4 full adders. Here we apply A1 and B1 and the carry n to the S1. We should apply the carry out to the next full adder where it receives A2, B2, S2, and the carry to the next stage. Here we have some 3, and here A3, B3, again a carry to the next stage, A4, B4, sum 4, and this is the carry out. This is a 4-bit binary parallel adder. It can add a 4-bit number A with another 4-bit number B and generate a 4-bit sum S and carry out. We can draw 4-bit binary parallel adder. Here 4 bits from A, 4 bits from B, as we draw, carry in, 4 bits the sum and carry out. This is the graphic symbol diagram for a 4-bit binary parallel adder. Really, if we want to add 8-bit number with another 8-bit number, we need two. This is 4-bit binary parallel adder. Now we need to add 8-bit number 8-bit adder. We can use 4-bit 4-bit binary parallel adder, and here another 4-bit binary parallel adder, binary. We apply to the first the 4 bits from A, the first 4 bits from A and B. This is carry in. Here is the sum, and apply the next 4 bits from B and A. This is sum, and this is carry out. So here we use two 4-bit binary parallel adders to sum an 8-bit number with another 8-bit number, and we obtain a 8-bit binary parallel adder. If you need to add 12 or 16, you need to use more. Usually, for example, 8-bit binary parallel adder and 4 are available on ICs. So if you need to add 16-bit number, 16-bit numbers, you need two 8-bit binary parallel adders organized in this manner. This is our binary parallel adder, 4-bit, and this is a good circuit really for subtract. Here the circuit can add or subtract depending on the control M. If M is 0, add. If M is 1, subtract. We are using 4 full adders cascaded in this manner. We apply AIs to the first input and BI to an exclusive OR with the M control as a second input to receive the sum or difference and the carry to the next stage. If M is 0, then 0. If M equals to 0, BI exclusive OR 0 will not change BI. So it works as adder. The output of exclusive OR is equals to the BI, and it works as usually as a full adder, and here we obtain the sum of the numbers. However, if M equals to 1, then BI exclusive OR 1 will result in the complement of BI. So here we obtain the ones complement, and since M is applied to the first, so complement of B, 1's complement of B, plus 1 will output 2's complement. So if M is equal 1, we are adding A to 2's complement of B. And this is equivalent to A minus B. A minus B. If M is 1, then we are performing subtraction. If 0, we are adding. The last thing here I'd like to mention, what is this gate, exclusive OR gate. You see, we have the carry to the last stage and the carry from the last stage. These carries are exclusive OR. If B is equal to 1, then we have overflow. If the carries are different, then we have overflow. But if they are equal, then we haven't any overflow. And we explained this in the lecture of representing signed numbers. Now BCD Adders. BCD Adders. Suppose we want to add two decimal digits coded in BCD. You remember the decimal digits 0, 1, 2, 3 up to 9 coded in BCD. We need 4 bits, etc. The remaining 6 are unused. There are 6 code combinations from 1010 up to 1111. And remember, in any design procedure, if you have unused code combinations, you can use them as do not care conditions in the K-maps. You can take them as 1 or 0. These are the decimal digits. If we are adding two decimal digits, for example, 3, which is 0011, with 4, the BCD code for 40100, 1110. The result is 7 in BCD and everything is okay, no problem. If we add, for example, the second case, if the result, remember, the result here is less than 10 and we haven't any carry. Let's add, for example, 6 with 7. 6 is 0110 and 70111. This is this BCD code for each of them. 1, 0, 1 with carry 1. Although we haven't carry out here, but the result is incorrect. There is no BCD digit like this. And really, you know, if we add 6 in decimal to 7, the result is 13. And 13 in BCD is represented as 0011, 0001. And this is not the correct result. So in this case, we have to adjust the result. Adjusting the result, we need to add to the result 6. This is the difference between the 16 and 10, since 4 bits represent 16 cases and the decimal digits are 10. So if we add 6 to the result, 1, 1, 0, 0 with carry 1. Now everything is okay. We have a 3 here and we have 1 here. So the first case, when we need to represent, to adjust the result, if the sum is larger than 9 and no carry, and of course 15 or less, if we haven't any carry. If the sum is 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1. In these cases, and no carry, we have to add 6. Another scenario, let's add 8 with 9, for example. 8 1 0 0 0 in BCD, and 9 is 1 0 0 1. Here we have 1 0 0 0, and we have a carry here 1. 8 and 9 is 17. So our result in this case is incorrect. Since we have a carry, again we need to adjust by adding 6. 1 1 1 0, and here is our carry. So now the result is 7 1 17, and this is okay since we are adding 8 with 9. You see, we usually have carry when we add 8 with 8, 8 with 9, 9 with 8, or 9 with 9. So in the design of BCD adder, we have to adjust the result if we have a carry, or if we have one of these combinations with no carry. How to differentiate any of these cases from the other sums, from 0 0 0 to 1 0 0 1? I think I have the table. If not, I wrote all the 16 states that we can generate from 4 bits. The first 9 are valid BCD digits. These are invalid digits. Now, if the sum is one of these, then no correction is needed. If the sum is one of these, or if we have a carry, then a correction is needed. A correction, we add 0 1 1 6 to the sum obtained. How can we differentiate any of these cases from these cases? If you look carefully, you note that in these cases we have 1 here and here, or here. And this is not true for any of these cases. The 2 cases that we have 1 here, we haven't 1 here or here. This condition can be used for adjustment. We'll go back to the circuit. This is a BCD adder. It is used to add two decimal digits coded in binary. So we have 4 bits for each digit. This is BCD, first BCD for A, and this is for BCD for B. They are applied here, and we have here the sum. This is the carrier. Now, how to adjust? These sums are applied to the next 4-bit binary parallel adder. You see, it's no carry, or the output of this block is equal to 0, then we will have all zeros here and no adjustment will happen. Adding 4 zeros to this sum will output the sum from here as it is, and no correction. However, if there is a carry from here, then this will be 1. 1 will be applied here, and 0, 1, 1, 0. So we add this value to the sum. This value is 6, meaning we are adjusting the result to obtain the final correct result. We have a bit, like in this case here and here, then we need to adjust all here. Then the output of this gate will be 1. Otherwise, it will be 0. Look ahead, carry look ahead adder. I will draw the binary, 4-bit binary parallel adder, also called rebel carry adder. Rebel carry adder because it rebels the carry from one stage to another. What are the problems of rebel carry adder? Do you see, we cannot receive sum here until the carry from here is generated, and we cannot receive the sum until we have the carry. Again, we cannot receive the sum until we receive this carry. So there is a delay. Carry look ahead adder is accelerating the process of obtaining the sums. Do you see, first note, A3 is 1 and B3 is 1, then carry 4 will be 1 regardless of the previous carries. In one full adder, and you remember the expression for adding 3 bits together, the sum is exclusive OR of the 3 bits, and the carry is AB, AC, BC. The carry is 1, both bits AI and BI is 1. This is the case, regardless of CI. Or if we have one of the two inputs, AI or BI is 1, and carry N of previous stage is 1. We can rewrite the carry, this is the sum, in this form. CI, AI exclusive or BI, or AI, BI. And now we define 2 variables. This is called carry propagate, and this is called carry generate. Accordingly, we can rewrite the expression for sum SI equal BI plus CI, and carry out CI plus 1 equals CI, BI, or GI. A 4-bit carry block head adder can be constructed with the help of the following steps. Generate all BI and GI internal signals. These can be generated simultaneously as C0 and all inputs are available. Just C0. Generate all carry output signals C1, C2, C3, C4. This will be valid after 3t time. Generate some signals, some B exclusive or C. This will be valid after 4t time. This is one possible circuit for a 4-bit carry lock ahead adder. The expression C1, G1, or C0, B0, C2, now we write it, equals G1, or G0, B1, or C0, B0, B1, C3, and C4. Note here, for example, in the expression of C4, we have in C2. For in the expression of C4, we have in C3. Here B0, G0, B1, G1, according to the previous expressions. And using this, we can generate the sum, which accelerates the process of generating the final sum, and which is better than rebel adders. Assume, as I mentioned, that T is the delay of a single 2-input gate. On rebel adders, we have a total delay 2n plus 2 multiplied by t. So, but in the lock ahead adder, we have 40. So, if here, if we have n equal 4, then 8 plus 2, we have 10t. Comparing with 40, the performance of the carry lock ahead adders is better than in rebel adders.